So we'd like to do an example of a proof that a function is surjective. So let's look at a function, a comfortable function. So f from the reals to the reals defined by f of x equals x cubed. So this function is surjective. One way to see that it's surjective is to look at its graph. Okay, there goes my lead. So the graph of this looks, roughly speaking, like this. And as x goes off to infinity, the y values go off to infinity. As x goes to negative infinity, the y values go down to negative infinity. It's a nice continuous function, so there are no gaps. So any place you set your pencil down on the y-axis, you'd be able to find an x that gets sent to that spot. So this thing is surjective because everything in the reals has something sent to it. So we want to prove that this function is surjective, which means we need to prove that the image of f is equal to the real numbers. So this is a set equality proof, and we've been doing set equality proofs for a while now. We know that means we have to show two things: that the image of f is a subset of the reals, and the reals is a subset of the image of f. So both of those things we need to show, sort of. This one is true by the definition of image of a function. So this is the one we really need to prove. So we have a subset proof to do. So I'm going to have to start by placing something in the first set and show, logically conclude, that that element that we placed in here must also be in here. So that's the definition of a subset, and that's how you prove the subset relationship. So I'm going to have to start my proof, and I'm just going to do an outline right now. So I'd let y be in the reals. And then you want to say blah, 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 and where you want to get to is that y is in the image of f, and that will show this subset relationship. Okay, so, we've done proofs like this before, so sometimes it's easy to work from the top down, sometimes it's easy to work from the bottom up, sometimes you work from a little bit from the top and a little bit from the bottom until you get them to meet in the middle. So I think this one's probably going to work from the bottom up best. So what does it mean for y to be in the image of f? How do I show that? So if y is in the image of this function, y is in here, and if y is in the image of this function, then there's something in the domain that gets sent to it. So that would mean that there exists an x in the domain, in this case the reals, such that y equals f of x. But f of x is equal to x cubed, so y would have to be equal to x cubed, which would mean, if you solve this equation for x, you'd get the cube root of y is equal to x. So if y is in the reals, the cube root of y is in the reals, and when you plug the cube root of y into f, you'd get y back again. And so that's sort of an outline for the proof. So that's the logic. The logic is fairly straightforward, and then there's the issue of actually writing up the proof. Let me get a clean sheet of paper, and we will do that. Okay, proof. Let f from the reals to the reals be defined by f of x equals x cubed, and let y be in the reals. I don't think I'll bother introducing another variable here. I'm just going to say then the cube root of y is in the reals. So we know this because if y is a real number, you take the cube root of real number, you get a real number. So this is the statement I can make just by properties of real numbers. And then I can say since f of the cube root of y is equal to the cube root of y cubed, which is equal to y, we have y is in the image of f. Period. So we have the cube root of y in the real, so it's in the domain, and when I plug this function in the domain, this element in the domain into the function, I get my y that I started with. They're just placing in the reals. So let me say this. So I have the subset relationship. I started with y in the reals. I ended up concluding that y is in the image of f. So we have the reals are a subset of the image of f. By definition, so I need to get both directions. And I'm not going to prove that the image of f is a subset of the reals. I don't need to. It's just by definition of the image of a function. The image of the function always has to be a subset of the codomain, and the codomain here is the reals, so we have the image of f is a subset of R. Therefore, I have the subset relationship in both directions, so the two sets are equal. So the image of f is equal to the reals. And we have f is surjective. Done. Oh, sorry. So that's an example of a proof that a function is surjective, and that's in general how they'll work. If you need to prove that a function is not surjective, which we already did in the previous video, you just have to find an element in the codomain that doesn't have anything sent to it from the domain. Okay, very good.